Hi Math 215 students. In this video we're going to do the first of 2 or 3 parts of section 1.4, and we're going to introduce the matrix equation AX equals B. So here are our outcomes for this video. Before moving on, please do your best to define those terms, to determine whether a matrix and a vector have appropriate sizes for multiplication and actually do the multiplication. Explain how the matrix equation and the vector equation are related, how they have the same solution set and which augmented matrix goes with these. And then again, we'll emphasize you want to be able to perform correctly a multiplication of a matrix and a vector. All right, so we talked in past videos about other perspectives from which we can understand the problem of solving linear systems. And this is another video in that vein. This will be the second of the alternative perspectives we've seen. The first one was the vector equations that we talked about in previous videos, and this will be the last one we'll run into for chapter 1, matrix vector multiplication. Now there's a line in your textbook that is important and will become more important to you as you get a little bit deeper into the course. But a fundamental idea in linear algebra is to view a linear combination of vectors as the product of a matrix and a vector. Now, if I were you, I would take the hint and try to focus in on this linear combination connection to the product of a matrix and a vector. It's right there in the definition, we'll see it right away, but it's an important idea that will help you if you keep it in mind in the future. All right, so let's talk about a matrix times a vector. Now, we're going to define it this way. There's nothing that says it has to be this way other than our definition. And so, given a matrix A with n columns, which we'll think of individually as being the vectors A1, A2 through AN, so there are n columns in the matrix A here, which is pictured on the left, and given a vector x in Rn, so it also has n entries, a first entry, a second entry, all the way through the nth entry, we're going to define what happens when we multiply this matrix by this vector to be this. We're going to take the entries of our vector and we're going to attach each of them to a column vector from A, just using scalar multiplication, and then we're going to add together those results. So if you want to see a more pictorial representation, you can think of it this way. We're taking column 1, multiplying it by entry 1 from the vector, column 2, multiplying by entry 2 from the vector, and so on up through column n multiplied by the last entry in the vector, and we add together these vectors. So if you take a look at what this looks like, you have a scalar times a vector plus a scalar times a vector, and we've seen something like that recently. We're going to get the product A times x by forming the linear combination of the columns of A that we get when we use the entries x1 through xn as the coefficients. Now the order of those coefficients is important, so you attach the right entry to the right vector. But just taking a look at this, our matrix times our vector is defined to be the same thing as a linear combination. All right, let's take a look at a couple of examples. If we were to take the matrix 1, 2, 3, 4, 5, 6 and multiply it by the vector 1, 0, 1, negative 1, the first thing we need to check is that the multiplication will work. We do need to have the same number of columns in A as entries in the vector. If you don't have that, you're going to be in trouble. Okay, but let's do that multiplication. We'll take the first entry 1 and multiply it onto the first column vector. The second entry 0 times the second column vector. The third entry minus 1 times the third column vector. And doing that scalar multiplication, this will turn into 1, 4. This turns into 0, 0. This turns into negative 3, negative 6. And adding that all together gives us a grand total of negative 2, negative 2. So negative 2 is the answer when we multiply this matrix and this vector. Now one thing to keep in mind, you do need to have the same number of columns in your matrix as entries in your vector. And what you'll find is that the size of your answer, it will be a single column vector, and it will have the same size as the columns. So if these are columns with 2 entries, the answer will have 2 entries. And that's just because you're forming that answer by doing a linear combination of those columns. Now here's our second example. We'll take this matrix on the left, shown here, and multiply it onto the vector 2, 5. Now this you'll notice that the sizes of these matrices and vectors can be look a little bit off from each other. The important thing to notice, though, is that we have 2 entries in our vector and 2 columns, so the definition will work. 2 times the first column plus 5 times the second column, and if you do those multiplications and additions, you'll end up with a grand total of negative 1824.3 as the answer to this matrix times this vector. All right, now here's a problem that turns our perspective around a little bit. We're asked to write a linear combination as a matrix vector product. So instead of taking the matrix and doing the multiplication onto the vector and getting something like this, we want to go backwards. We want to find a matrix A and a vector X that will produce the same thing as this linear combination. So if you want to, take a second to kind of figure this out on your own. What's the matrix A? What's the vector we're multiplying by? If you want to pause the video, that's great. We'll answer it now. Okay, so one thing we want to remember is that the columns in our linear combination come from the matrix A. And so our matrix A will have those same columns in that order. And if we take 2, -1, and 7, they're scalars, as the entries of our vector, then this matrix vector product will give us the same answer as this linear combination there. All right. Now, we've been talking about different types of equations. We started off the course talking about linear equations, where you had scalars times unknown variables, and then you were supposed to have those equal to something on the right-hand side, and we had to solve this linear equation, a system of linear equations, and we talked about how to do that. Next, we introduced a vector equation, where you have vectors, v1, v2 through vn, and you have a vector b. And the question here was usually, what should the coefficients be? What should x1, x2, and so on through xn be in order to make this equation true? We talked about how to solve these a little bit. And now we're going to introduce another type of equation, ax equals b. Now here, A is a matrix, x is a vector, and b is another vector. And just like we had to in the vector equations, usually what we want to do is solve for the x1, x2, and so on. And here, those are entries in the vector x. So the vector x is usually the thing we're solving for in this matrix equation. A and b are given to us. All right, so now let's see this in action. And actually what we're going to do is another one of those perspective changing problems. We've got a linear system shown here, and we want to write it as a matrix equation, ax equals b. All right, now as we start, remember our previous problem there, ax, that was supposed to represent a linear combination. And so these aren't vectors here. We can't really form linear combinations, but maybe this gives us a hint. We want to write this in a vector equation form. So let's do that. If you want to, you can go ahead and pause the video and work that out. But what I will do right now is notice that I've got x1 in all of the first column entries, x2 in all of the second column entries, x3 in all of the third column entries. So maybe if I factor those out as multiples on the vectors 2, -1, x2 times 1, 0, and then I have x3 times -4, 2, I can write that left-hand side of the system as a vector linear combination. And if I do that, I might as well do it on the right-hand side, put the 0, 5 in a vector, so that it turns into a full-blown vector equation. Now we just got done talking about how to turn a vector equation into a matrix equation, so let's do that. Remember, the vectors in our linear combination turn into the columns of our matrix. The x1, x2, x3 become the entries of our unknown vector. And if we have an equals 0, 5, well, so be it. We'll carry that down as a 0, 5 there. And as you look at this, this is a matrix equation. We have a matrix times an unknown vector equal to a given vector, ax equals b. Now, let's pause just a second to think about what this means. This means that for any vector equation and for any system of linear equations, you can translate any of those into this matrix vector equation, this matrix equation. And this will be handy for us, as we'll see in the next couple of videos. Thinking of AX in particular gives us a whole bunch of questions we can ask and answer about linear combinations and about working with vectors and later on vector spaces in general. So how would you solve this matrix equation? Well, the good news, if you want to pause and think about it, go ahead. But the good news is that we already know how to solve this. And actually, if you think back to this, the second line, the vector equation, how did we solve those? If we can solve that one, we probably will have an answer to the matrix equation. And then if you think back a little bit further, we solved vector equations by writing out the linear systems they corresponded to. So to solve this matrix equation, what you would absolutely do is write out the linear system that it corresponds to, because we know how to solve linear systems. You can form an augmented matrix, you can row reduce, and everything that you have in your toolbox to solve this linear system. And whatever you get for x1, x2, and x3, that will be what you should put in your vector to solve the matrix equation. All right, so there's definitely connections here. We've talked just now about the connection between matrix equations and vector equations. We saw that those were both connected to linear systems, and our definition of matrix equation defined AX as the linear combination of the columns of A, and so writing B as a linear combination of given vectors is definitely connected to matrix equations. And to solve all three types of these equations, we use the augmented matrix. We've talked about having solutions. We want to no pivot column in the last column of our augmented matrix, and if we don't have a pivot in the last column, we'll have a solution for the linear system for the vector equation. What about the matrix equation? Well, that's our theorem here. The big connection is that if A is a matrix with those columns A1 through AN, and those columns each have M entries there from Rm, then the equation AX equals B has the same solution as the vector equation x1a1 plus x2a2 plus ... plus xnan equals B. So the same solutions will exist for the matrix equation and for the vector equation. And of course, to solve to find those solutions, what we want to do is solve the linear system that goes with them, the linear system whose augmented matrix is formed from those columns as the first n columns, and then B carried down as your right-hand column of that augmented matrix. So the key word is same. We get the same solutions doing it this way as doing it this way as doing it this way. And so the solution sets are exactly the same. And so we've, in this video, talked about a different way of thinking about linear systems. We've introduced the matrix equation, and that will give us another valuable perspective from which to understand things. It's a fundamental idea, and I encourage you to internalize it as you go along. So here are the ways to internalize that. These are the outcomes you want to make sure that you can do before moving on. And with that, we'll end the video, and we'll see you in part B.